أهلا بيكم. Today we're going to continue our talk about the ear by studying the inner ear. So let's begin. After completing the learning about the external and middle ear, now we are encountered with the inner ear. Actually, the inner ear is um, um, a series of carvings inside the bone to form what's so-called the bony labyrinth, and it's almost filled up with a continuous duct system that doesn't completely occupy the space inside within the bone. It's called the membranous labyrinth. So we have a bony labyrinth filled up, almost filled up with a membranous labyrinth. The bony labyrinth is lined by periosteum and filled with fluid with similar structure like the extracellular fluid. Means it has high concentration of sodium and low in potassium. On the contrary, the duct system, the closed duct system, has fluid inside it called the endolymph, and it's similar in structure with the intracellular fluid. Means it's rich in potassium and low in sodium. Okay, now if we are talking about specialities here, the part of the membranous labyrinth, which is the cochlear duct, is the organ of hearing, and the rest, which is the utricle, saccule, and the semicircular ducts, are the organ of balance. And of course, all the impulses are carried by the vestibulocochlear nerve, as you can see here. Okay, let's start with the details. The bony labyrinth is thrown into three parts. Middle part is called the vestibule, and connects the cochlea anteriorly and semicircular canals posteriorly. And from the vestibule, there is a canal that goes backwards called the vestibular aqueduct to open behind the petrous bone. See, it goes through the bone and opens behind the posterior surface of the petrous bone. This canal, the vestibular aqueduct, is filled up with what's so-called the endolymphatic duct, which has a reservoir, a sac-like reservoir at the back of the petrous part of the temporal bone, and is connected to utricle and saccular parts of the duct system. The semicircular canals, we are talking bony labyrinth now, canals, not ducts, are three semicircles perpendicular to each other. Two of them are vertical, like the anterior semicircular canal, anterior or superior. You may call it superior. Posterior semicircular canal, and the horizontal one is the lateral semicircular canal. See, one horizontal and two vertical. Note that the ends expands into bulbs. Okay, and they all open into the vestibule, and it's put inside the skull in a way that, see, this is the anterior and posterior and lateral of the right side. The anterior of the right side is continuous with the posterior of the left side, and the anterior of the left side is continuous with the posterior of the right side, and the two lateral semicircular canals complement each other. So you are guaranteed this way to balance within 3 dimensions. That's why we have 3 canals, by the way, because it's 3 dimensions, and because it measures kinetic equilibrium during movement. So it is in a form of semicircle. For any diameter represents a movement. So we have infinite number of movements that we can balance. We can balance by our brains. Okay. So remember that the anterior complements the posterior of the other side, the posterior of this side complements the anterior of the other side, and the two lateral complement each other to have a balance within a complete sphere. You got the point? It's easy. Okay, the cochlea is about 2.5 to 3/4 of a turn around a central modulus. This is the modulus. Of course, the modulus is already taken up by the fibers of the cochlear nerve, as we will see later, but it still was the original axis around which the bone made 2.5 or 2 3/4 of a turn. And from this modulus, a lateral spiral lamina, see that? Lateral edge spiral lamina goes through all the turns of the cochlea, and to this spiral lamina will be attached the membranous labyrinth of the cochlea, which is the cochlear duct. Okay, the cochlear duct is arranged so that it attaches to the lateral side of the cavity inside the cochlea, turning it into 3 compartments: scala vestibuli, scala tympani, and the duct itself is scala media. Okay, the scala vestibuli and scala tympani, the 2 cavities formed by the arrangement of the duct system inside, they are continuous at the apex of the cochlea. This area slit-like continuation of the scala vestibuli to the tympani means that if I am going with the scala vestibuli upwards, I end up coming back downwards on the scala tympani to its end. Okay, this is what I mean. They are continuous. The point of that they connect or are continuous with each other at the top is called the helicotrema. So the helicotrema connects the scala vestibuli with the scala tympani. You know what I'm getting to now. Okay, so actually you have 3 cavities inside. One of them is the duct itself, and the surrounding 2 are the scala vestibuli and tympani. The vestibuli, if you go up with it through the helicotrema, you will continue down back on the other side, which is the scala tympani. And remember, the scala vestibuli began where the oval window is, and the scala tympani ended where the round window is, which has a membrane on it. Okay, understand this to be able to understand the mechanism of hearing. Okay. There's a small canaliculus near the round window that opens into posterior cranial fossa to allow connection between the CSF and the perilymph, occupying the bony labyrinth. Okay, what else? The membranous labyrinth. We know that it's a continuous duct system, has a cochlear duct, that fills the cochlea, has utricle and saccule that fills the vestibule, and has 3 semicircular ducts that ends up in an ampulla and fills the semicircular canals of the bony labyrinth. Now, the organs of balance. Balance means we're talking about the contents of the vestibule and the semicircular canals. That's the utricle, saccule, and the semicircular canal. Now, the utricle is superior or above the saccule and are connected by a duct called the utriculosaccular duct. This utriculosaccular duct branches and leads to an endolymphatic duct that runs in its own canal and opens at the posterior surface of the petrous bone as the endolymphatic duct and sac. Okay, we have mentioned this before. The receptors in the utricle and saccule and the semicircular ducts, they detect changes in position and linear acceleration. Utricle and saccule is concerned with the static equilibrium. Static equilibrium means the position in space. Position in space, especially position of the head in space, because the body follows the head. And the receptors in the semicircular ducts are for kinetic equilibrium. Kinetic equilibrium means equilibrium during movement. Kinetic equilibrium means equilibrium during movement, linear acceleration during movements in different directions. And that's why they are three, to cover the three dimensions, and semicircles because every diameter here represents a point of movement. So we have infinite movements that we can balance within. Okay, the receptor in the utricle and saccule is called the macula, and the receptor in the semicircular ducts is called the crista ampularis. Okay, the utricle responds to linear acceleration in the horizontal plane and sideways head tilts, while the saccule responds to linear acceleration in the vertical plane, means forwards and backwards and upwards and downwards movements. And it's said that the saccule responds for both accelerations, like the ones in the vertical plane and horizontal plane as well. Okay, but for sure the utricle is for the horizontal and the saccule is for the vertical. Okay, the crista ampularis, which is the receptor for the semicircular ducts, responds to rotation and movement in any direction. See how perfectly designed this device for equilibrium. The organ of hearing, which is present in the cochlear duct, is this organ. Now see, this is the duct itself. This is the duct itself. See, this is the duct itself. It's triangular in cut section, attaches to the lateral wall, turning the cavity into scala vestibuli, scala tympani, and scala media. Scala media filled with endolymph, which is the duct, and scala vestibuli filled with perilymph. And vibrations, mechanical vibrations, run through the liquid and reaches this part of the duct and produce the electric impulse in response to the mechanical wave arriving. This is the site of transduction between mechanical vibration and to become an electrical impulse by an organ called an organ of Corti. You see, one side of the tube is called the vestibular membrane that separates the scala media from the vestibuli, and this is the one actually that vibrates and conducts to the basilar membrane. This is the basilar membrane. See, this is the basilar membrane extending from the spiral lamina, coming from the modulus to the lateral wall. See that? This is the basilar membrane. And on top of the basilar membrane is the organ of Corti, the organ of hearing, which you can see a tunnel here. This is called the tunnel of Corti. This is a tectorial membrane, fixed membrane, against which hair cells with processes gets compressed when the basilar membrane vibrates. Whenever it vibrates, it compresses the cells on it against the tectorial membrane, and this is the point at which transduction occurs, the transduction of the mechanical impulse into an electrical impulse. Okay? This is called the spiral organ of Corti. What happens is the vibration reaches through the scala vestibuli, vibrates the vestibular membrane and the inside endolymph, which vibrates the basilar membrane. The basilar membrane with cells on top, touches against or compressed against the tectorial membrane, at which point an electrical impulse is traveled back through a nerve fiber to a ganglion in the modulus called spiral ganglia, and it's the same principle. You know, the cells, the sensory cells have their cell bodies in the spiral ganglia, and then the ganglia give rise to the cochlear nerve arising from the cochlea. Okay. Now, we mentioned the basilar membrane. This basilar membrane is not the same all over the length of the cochlea. It's narrowest and stiffest at the base turns, and as you go up to the apex, to the helicotrema, the basilar membrane expands, becomes thinner and wider at the top. So it's stiffer at the bottom, at the beginning, at the basal turn, and narrower and wider and more, or softens, least stiff at the top. It shows what's so-called the place principle, by which, imagine the membrane works as, you know, an area filled with sensitive points. On each point on this area, on this surface, has properties and changes in response to a certain frequency, characteristic frequency. So imagine as if you have this whole board of around 3 centimeters, 2.5 centimeters long in the cochlea, and with all dots on it indicating it, every single point indicates a characteristic frequency. This means that the wave coming will affect the basilar membrane in a way that the wave will travel along the membrane until it touches a sore spot, you know, a spot specific for that that frequency, this particular frequency of that wave, and the response is given accordingly. You know what I mean now. It's like a board of tones, of frequencies all over. This is called the place principle of the basilar membrane. About the vessels, the blood supply of the bony labyrinth is from the maxillary, like the anterior tympanic branch, from the middle meningeal artery, and the posterior auricular artery, and the arterial supply of the membranous labyrinth coming from the labyrinthine artery. The labyrinthine artery comes off the basilar, that is formed by the union of the two vertebral arteries in front of the pons of the brainstem. It gives a lateral branch called the labyrinthine that enters the internal acoustic meatus with the vestibulocochlear and facial to supply the membranous labyrinth through the branches inside it gives inside. Okay, the innervation, of course, we're talking about the vestibulocochlear nerve, and the nerve fibers coming from the organ of Corti, their cell bodies are in the spiral ganglion, and the spiral ganglion gives off the cochlear nerve. This is the cochlear nerve before it meets the vestibular nerve, which has the same story. The cell bodies of the sensory fibers coming from the receptors have their cell bodies in the vestibular ganglia before it joins into a nerve together with the cochlear to form the vestibulocochlear nerve. So we have vestibular nerve and cochlear nerve. So that's the vestibulocochlear nerve. Okay. Now we have an intimate relation between the facial nerve and the ear, and it does something in the ear. I mean, it supplies a muscle like the stapedius muscle, gives off branches like the chorda tympani. This is the chorda tympani. Okay, so it's important to know the relation between the facial nerve and the ear. As it enters the ear through the internal acoustic meatus, it crosses over the vestibule and to reach the medial wall of the middle ear and goes back and downwards to exit the skull. Now as it goes downwards, it gives off the stapedius to supply the stapedius muscle, and the chorda tympani, which pierces the anterior wall and exits through the petrotympanic fissure. You know the story of the chorda tympani, where it hooks up with the lingual nerve, reaches its destination, which is the tongue, anterior 2/3, to carry taste. Okay, another branch comes off the facial from the geniculate ganglion it forms. It's called the great petrosal nerve, and we know the story of the great petrosal nerve. After emerging from the middle ear, yes, it's joined by the deep petrosal and form the nerve of the pterygoid canal, and eventually synapse in the pterygopalatine ganglia. We have said this, that many times. Now, the transmission of sound, how does it work? Now we will deal with a vibration, single vibration, coming concentrated through the air pinna, and then concentrated through the canal, directed to hit the drum, the tympanic membrane. Now the tympanic membrane has a character which is called the faithful response. It responds adequate to the wave coming, without adding or subtracting any of its frequencies. Now we are still dealing with mechanical vibration here. The drum vibrated and controlled by the tensor tympani muscle that prevents excess vibration of the drum, and omits the low frequency sounds, like sounds of the background of the sound source, so to hear better. Now the tympanic membrane is much bigger than the oval window, so this difference in surface area will be reflected on the amplitude of the wave coming. It's like the principle of the hammer and nail. Why the hammer nails the nail? Actually, because the surface area of the hammer is much bigger than the head of the nail. That's why the nail sinks. The same applied here. It's the sound after reaching the inner ear is magnified around 16 times because of the different surface area, and about 1.4 times due to the action of the solid ear ossicles that articulate in synovial planes, synovial joints. So the sound was coming through air, hit solid, which will give a faster speed for sound to be propagated along the ossicles to the oval window that opens on the scala vestibuli. Now the stapes is also controlled by the stapedius muscle. Okay, so we have a control at the end of the mechanical and the beginning of the mechanical impulse in the middle ear. Okay, the same wave propagated and amplified reached the oval window. Now what's behind the oval window? Liquid media, the perilymph. It will travel through the scala vestibuli, because the oval window opens on the scala vestibuli, will vibrate the vestibular membrane and the endolymph inside and the basilar membrane, and a nerve impulse will elicit from the organ of Corti through the spiral ganglia, through the cochlear nerve, and to the brain. This is called the point of transduction, and how we convert the mechanical vibration into electrical one. So what's the use of the scala tympani? Now remember, we started an electrical impulse through the organ of Corti, but the mechanical vibration is still there because it's running in liquid media. Through the helicotrema, it will go through the scala tympani, and eventually at the end hits the round ligament, round window membrane, the membrane on the round window, which is the secondary tympanic membrane. So the membrane bulges off, and to absorb the excess part of the wave that we don't need, so as to get acuity and clearness of the sound, of the nerve impulse produced and the sound perceived. You know what I mean? So with every push on the tympanic membrane, the primary tympanic membrane, we end up with a push or bulge of the secondary tympanic membrane that covers the round window. Well, I hope I simplified a complex subject, which is the ear, especially the inner ear, and gladly I'll be reading your comments on this. Thank you very much for watching.